Alright, so got a little bit bogged down with the technical details here, but I think the correct way to do this is you actually build a multilinear map from the Cartesian product, R fold copies of the tangent space at gamma of 0, S fold copies of the cotangent space at gamma of 0. You send that into the Cartesian product space at gamma of t, the RS Cartesian product space at gamma of t, just component-wise by using these linear isomorphisms. And then this will, these are not like, these are vector spaces, but they're not, this is not like a, these vector spaces. Yeah. Okay, the point is that then if you send the image to the tensor product at the RS tensor bundle at gamma of t by just using the map which sends, okay, this is just the canonical map from the Cartesian product to the tensor product, which sends like in the case of R, let's say R equals 2 and S equals 0, this is just going to send V comma W to V tensor W, okay? So, right, so then our codomain is now the tensor product, and we're going to end up with a multilinear map from the Cartesian product into the tensor product at the Cartesian product at gamma of 0 to the tensor product at gamma of t. That's a multilinear map, and then it's going to factor through to the tensor product on the domain. Okay, but the point is we have a linear isomorphism of these. It's not a linear. Is it a linear isomorphism? Yeah, it's a linear isomorphism on the Cartesian product. Right. Yeah. And it should factor through to the tensor product. Okay, so the point is, this was kind of skipped in the notes. It just says, okay, we have this induced parallel transport from the tensor bundles. Okay, and you can define that explicitly by first constructing a map which is component-wise from the Cartesian product into the Cartesian product. Maybe. Please. Okay, into the Cartesian product. Kind of getting a little bit bogged down with the details, but I don't think this is pedantic. I think this is kind of important. And then we send this down to the Cartesian product. This is canonical map. Send this down to the tensor product. RS T gamma of T. Okay, so we start with all these parallel transport. We start with the parallel transport maps. P gamma of 0 t and this P star. Okay, so we start with these parallel transport maps. We can build a sort of isomorphism of the tensor bundles by first looking at the Cartesian product space, sending it to the Cartesian product space at gamma of t. So we start with the Cartesian product space at gamma of 0, send it to the Cartesian product space at gamma of t, and then factor this the codomain through, compose it with the canonical isomorphism var phi to the tensor bundle, or I guess to the not tensor bundle but the tensor product of these tangents, R tangent spaces, S cotangent spaces. And then from here, through this composition, we get a multilinear map. Okay, and this multilinear map is going to factor uniquely through to the tensor product on the domain. Okay. that is how we build these parallel transports between the tensor bundles, the RS tensor bundles, and then we can define the covariant derivative using this parallel transport structure, just by defining, take the covariant derivative of a tensor field at t in the direction x to be, we evaluate t at gamma, we evaluate the tensor field at gamma of t, we parallel transport it back to gamma of 0 via the inverse p0t inverse, parallel transport the tensor field back to gamma of 0, subtract the tensor field evaluated at gamma of 0, and then divide by t, and take this difference quotient, take the limit as t goes to 0, and that gives us our of the covariant derivative here, okay? Where, again, gamma has to be a curve which agrees with the vector field x. So gamma has to be a curve such that gamma of 0 is p, and gamma prime of 0 is x evaluated at the point p, okay? So this is like our intuitive formula for what this covariant derivative should be. And then we can do the similar kind of computation as we did previously for the single covector field. And this is kind of an exercise which I should do and have not done. And then we get this computable formula, okay? So this is the formula to kind of memorize, okay? So we have that this nabla xt evaluated on R covectors and S vector fields is going to be, first, we take the covariant derivative of just the smooth function given by evaluating the tensor field at these R covector fields and S vector fields. So we evaluate the tensor field, we get a smooth function, we take the covariant derivative of that smooth function, and then we subtract the sum of basically t evaluated, the tensor field evaluated at all of these covector fields, but we replace the ith covector with its covariant derivative with respect to x, and similarly we replace the vector field y sub j with the covariant derivative with respect to x, that component, okay? All right, so this in words, the covariant derivative of a tensor field in the direction x is going to be, if we evaluate that, it's now, okay, covariant derivative nabla x of t, okay, is another RS tensor field. If t is an RS tensor field, nabla xt is another RS tensor field. To evaluate this new RS tensor field, we take in R covectors and S vector fields, R covector fields, S vector fields, okay? Okay, and then the formula is nabla x of t evaluated at these R covector fields and S vector fields is essentially nabla x of t evaluated on all those vector and covector fields. So that's just nabla x of the smooth function, okay? And then minus the sum of t evaluated at all of these R covector fields and S vector fields, but we sum and replace each component term by term. We replace each component with the covariant derivative of that component, covector field or vector field. We replace that component with the covariant derivative of that component in the direction x, okay? And we subtract that, okay? All right, so here's the formula one more. Okay. And then we have this example where we apply this to the metric g, and we see that when we apply this to the metric g, we just get that first, okay, so nabla x g evaluated at two vector fields y and z. We first take nabla x of g of yz, so just nabla x of the inner product of y and z. Then we subtract g of nabla x of the first component, and leave the second component, and we subtract g of first component and then nabla x of the second component, okay? And notice here that this, interestingly enough, is if we set this identically equal to 0, we get the metric compatibility condition, okay? So setting this, the covariant derivative of the metric to identically equal to 0, the condition for metric compatibility, okay, which we're going to talk about later. Okay, so then the way to remember the formula for just the covariant derivative covector field is we're gonna take this we're gonna take essentially the contraction map, it's technically like the identity map, okay, which takes in okay, so we look at the identity map. I'm sorry, these videos are hard to make, bro. Okay, so now take a vector field and send it to itself, okay? That's the identity map, okay? So we have a identity map from smooth sections of the tangent bundle to smooth sections of the tangent bundle. We can view that as a 1-1 tensor, which takes in a covector field and a vector field, and then just evaluates the image of the vector field with that covector field, okay? So that gives us basically the identity map. We can view it as a 1-1 tensor, which sends omega comma y to omega of y, okay? Now, the condition that this identity map is parallel means that we take the covariant derivative of this identity map, nabla x of I, evaluated at omega and y, and we set that equal to 0, okay, to require that the identity map is parallel. But using this formula for the covariant derivative of tensor field, we have that nabla x of I is equal to nabla x of I evaluated at omega comma y is equal to nabla x of, just evaluate the tensor, so now we get nabla x of omega of y minus I of nabla x omega comma y minus I of omega comma nabla x y, okay? And now I is just going to contract the omega with the y, okay? So we can rewrite this formula as nabla x of omega of y minus nabla x omega of y minus omega of nabla xy, and we set that identically equal to 0 to ensure that the identity map is parallel. And that gives us the formula for nabla x of omega, namely nabla x omega of y is equal to x of omega of y minus omega of nabla xy, okay? All right, so that's a way to remember, that's a nice way to remember the formula for the covariant derivative of a covector field, okay? All right, now this is an important section. So now we're going to talk about compatibility, okay? So turns out that this way of kind of inducing the linear connection, given a linear connection on the tangent bundle, we can induce a linear connection on the tensor bundle, and turns out that this way of inducing the linear connection on the tensor bundle is special because it's actually a derivation on the tensor algebra, okay? And what that means is that it's compatible with the tensor product, okay? So if I take the covariant derivative nabla x of, let's say, y tensor omega, okay, then this is equal to nabla x y tensor omega plus y tensor nabla x omega, okay? So essentially, this covariant derivative operator, nabla x, when we induce it on the tensor bundle in the fashion that we've described for an overly long time at this point, kind of dragging it out, we can solve and recognize that, in fact, this covariant derivative, this induced covariant derivative, satisfies a product rule with respect to the tensor product. Okay, so let me just show you that one. Okay, so we see here, nabla x of y tensor omega is equal to nabla x y tensor omega plus y tensor nabla x omega. It satisfies a product rule. Okay. All All right, so that's really important, and you can pause the video and look at this example to see the derivation of this, okay? All right, so the other key thing is that it also commutes with the contraction operators, okay? So the contraction operator, C superscript I subscript j, so C superscript I subscript j, this contraction operator, what it does is it takes the ith, so if you have an RS tensor, okay, it's going to take the ith component of the, like, if you think about R as like RS tensor field, you have like R vector fields and S covector fields, but they're all tensored together, right? So it's going to take the ith, vector and the jth covector and pair them together. That's what C superscript I subscript j does. Way to remember that is C superscript I subscript j of partial subscript I tensor dx superscript j, right, is just going to be 1 in coordinates, okay? That's a coordinate way to remember that. But the point is that we have these contraction mappings, C superscript I subscript j, which take the ith component vector component, the jth covector component of the tensor. It's not component, it's like, if you lift it to the Cartesian product, then it's the ith component of the vector and the jth, so the ith vector field and the jth covector field when you lift to the Cartesian product. This is the contraction mapping, Cij. The point is that the covariant derivative commutes with the contraction mapping, okay? And so we can see the derivation of that here, okay? So it has to do with the fact that the identity map is parallel, okay? Okay, so it's also an exercise to show that these contraction mappings commute with the covariant derivative, okay? So the point is that given a linear connection on the tangent bundle, the induced linear connection, okay, on the tensor bundle is compatible with the tensor product operation in the sense that it obeys a product rule with respect to the tensor product, and it commutes with all the contraction mappings, okay? So let's just show you this, and you can show that in fact this induced linear connection is the unique linear connection which obeys these properties 6 and 7, these compatibility with the tensor product and commutes with the contractions. So these properties 6 and 7 actually are unique to this induced linear. This induced linear connection is actually somewhat special, okay? All right, so that's theorem 1.4 is actually, yeah, so this is unique. It's unique in the sense that, remember, we required, the key other point that we required at the start of all this was that on the 0, 0 tensor bundle, which is just a set of smooth functions, we required the canonical linear connection nabla x of f is equal to xf. You required that. When you require that, so nabla xf for a smooth function f is equal to xf, and then you require the two compatibility conditions compatible with the tensor product, basically obeys the Leibniz rule with the tensor product, and commutes with the contraction mappings, then there's a unique linear connection on the tensor bundle which coincides with the given linear connection on the tangent bundle, and it's exactly given by these formulas that we've been describing for the past long period of time. Okay, so now when we come back, we're going to start talking about the Hessian of the function.